today we will be going over molecular equations and how to write them, and in what order they are written, in the compound form as well as ionic and net ionic equations. So let's get started. We are going to be going over the end of chapter 4 questions. And these will be questions 5, 7, 11, and 30. There's not too much this week since it's just balancing equations and that sort of thing, but it's really, really important because this is something you'll be using a lot over your chemistry experience and possibly careers. So let's get started. So we have question 5a to begin with. Before we get into question 5a, actually, it's important to check in this order. If you can see right here, I already wrote this down. When you are checking balanced equations, or when you are making a molecular equation balanced, you want to check these in order. So you want to look at polyatomic ions first, because those are very specific to, they could be two different atoms in that polyatomic ion, and so recognizing, that's not just two separate ions or two separate atoms, it's actually, a polyatomic ion. It's important to check that, because then it will be easier for counting up the charges to see if something is balanced and is neutral or not. So polyatomic ions are first, and then you need to check metals second, and then nonmetals. And then the nonmetals does not include hydrogen and oxygen. So that's number 1 here, number 2, and then number 3 nonmetals, and then hydrogen and oxygen, and then diatomic elements, because if you have a gas that's just alone, so if you have chloride gas, all you have to do is just put a coefficient in front of it to balance it at the last step, because it's just alone itself. So it's really, really easy to balance only one atom when it's by itself. So that's why it's last. Okay, so that's the order we want to check things in. Let's go over 5a. So we have a solid calcium carbonate is heated, and it is decomposed to a solid calcium oxide and carbon dioxide gas. So in this problem here, we have calcium carbonate, and it decomposes, so this is what it will go to in the reaction. Solid, so it gives us the state of what it is, the solid calcium oxide. And then we have carbon dioxide gas, so it also gives us a state. As well as the first one, calcium carbonate, is also solid. So it gives us all the states that we need. Okay, so we have calcium carbonate, and so what that looks like is calcium, and that is a 2+ ion. I'm just going to list all of what we are given in the problem, and then we can put them together and make each compound neutral. I'll show you what that looks like. So we have calcium, we have carbonate, which looks like CO3, and that has a 2- charge. And then we also have solid calcium oxide. So that has a calcium, and we already wrote that. And an oxide has an oxygen, which is a 2- charge. And then we have carbon dioxide gas. And so carbon dioxide has another dioxide, so that's also oxygen. But carbon dioxide is CO2, and that's already balanced. But many of us already know what carbon dioxide looks like. Okay, so that's all of what we have in terms of what each ion we're working with or compound we're working with. So since we're starting with solid calcium carbonate, we have a calcium and a carbonate here. And since each of these, or the calcium has 2+ and the carbonate has a 2-, putting these together, 2+ and a 2-, that is a 0 charge, that's neutral, so we don't have to put any coefficients for any of these different, the atom or the polyatomic ion carbonate. So that's already balanced, and it's a solid state, and so then it decomposes, so then that's an indicator that it's going to be on the right side of the reaction. So an arrow here, and then calcium oxide, and so that's calcium again, and oxide, which is oxygen, and the ionic compound oxide. So calcium has a 2+, oxygen has a 2-, so 2+ and a 2-, it's neutral again, we don't have to change anything. And it said it was a solid in the question. So then we have solid calcium oxide worked out, and then it also produces carbon dioxide gas. So that's also CO2 here. And the reason why, I already wrote out CO2 because a lot of us already know, but the reason why I knew this is because carbon has a 4+ charge and oxygen has a 2-. And so since there is a 4+ for the carbon and only a 2- for the oxygen, we need 2 of the oxygens to neutralize the carbon, and so it's a net neutral charge. So that's why there's 2 of the oxygen. And we want to put it below here because this isn't it's not aqueous. So if it was, if this, we will get into net ionic equations here, but if this was, let's just say, an aqueous compound, then we could write it like the 2 oxygens here in front. But since we don't have that, and it's a part of the compound, we put it below here. So that's what that looks like. So all of these compounds are neutralized. We understand how to count different ones to make sure it's neutral. And remember to put all the states of each compound or atom or gas or whatever you have. So yeah, let's work on 5C. So 5C, hopefully you can see my screen. Yeah, awesome. Okay, so we have 5C and it says aqueous solutions. So that's an indicator of our state. We have aqueous solutions of magnesium chloride. So I'm going to write out what we're working with here. So we have magnesium, and magnesium has a 2+ charge as well. Magnesium chloride, so we're working with a chlorine, and chlorine has a only minus charge. And it says magnesium chloride and sodium hydroxide. So sodium is going to look like Na, and Na, sodium, has a plus charge, and hydroxide is a polyatomic ion that you are becoming more familiar with, and it has a minus charge. And it's also, it says it's going to react to produce solid magnesium hydroxide. We already wrote down what magnesium hydroxide is, and then sodium chloride, and we already got the sodium and the chlorine here. Okay, so these are the 4 different species that we're working with in this problem. So let's start writing out the left side of the equation. So it says aqueous solutions of magnesium chloride and sodium hydroxide. So these are the 2. And since we have magnesium and chloride, magnesium has a 2+ and chlorine has a minus. So we will need 2 chlorines to balance out the magnesium. And in the problem it says it's aqueous. So that's what that looks like. And then let's work on sodium hydroxide. So sodium hydroxide has sodium here, and then the hydroxide. And sodium has a plus charge, and hydroxide has a minus charge. So we won't need to put any number of sodiums and hydroxides other than 1 because it's already balanced. And they also said in the problem that it's aqueous. Okay, so that looks like that's the left side of the equation. And yeah, so that looks like it's the left side of the equation. And so let's work on the right side of the equation. So it says it's going to react to produce solid magnesium hydroxide and aqueous sodium chloride. So we have magnesium here, and then we have hydroxide. So that's the magnesium OH. But since magnesium is a 2+ and hydroxide is a minus, we will need to have 2 hydroxides. We'll zoom a little bit more. 2 hydroxides to balance this out. And since it also said it's solid in the problem, we'll put a solid right there. And the fourth compound that we're working with is sodium chloride, and it said it was aqueous in the problem. So we have Na, that's the sodium, and then chloride. And since sodium has a plus charge and the chlorine has a minus charge, we know that it's going to be balanced because 1 plus and 1 minus, so we don't need to change anything there. And this is going to be aqueous. So in the last problem, I didn't go over balancing the left and the right side of the reaction. It's already balanced, but for this one, we will go over balancing this because this is not a balanced equation right now, or a reaction. So let's write down all of what we have on the left and the right, and then count how many we have of each different thing. So this makes it easier for knowing how much we have of everything. So we have magnesium, we have chlorine, we have sodium, and we have hydroxide. And so we have the same things on the right because it is balanced on what kind of things we have, but not the amount of things yet. So it looks like we only have 1 magnesium here, and it looks like we have 2 chlorines here. So 2 chlorines. And then for the sodium, we only have 1. And then for the hydroxide, we only have 1 here. So that's the amount of things we have on the left. The ones on the right, for magnesium, we have 1 as well. For hydroxide, we have 2. So that's different than the left because we only have 1 on the left. So we already know we have to fix that pretty soon. For chlorine, we only have 1. And for sodium, we only have 1 as well. So we put the 1 right there. And so that's what it looks like on the left and the right. And so given that we have 2 chlorines over here and then 2 hydroxides, when we have less on the other side, we'll need to fix that. So since we don't have enough hydroxides on the left side, we're going to put a 2 in front of the sodium hydroxide. And so that will do is that will give us 2 of the, I'll put this here instead of dashes. So we have 2 of the sodium, and now we have 2 hydroxide. And so since now on the right we only have 1 sodium, we're going to have to put a 2 in front of here. So now we have 2 sodium, and then we have 2 chlorine. And so that's what that looks like. And it looks like this is balanced. So because we have an equal number of hydroxides, sodium, chlorine, and magnesium on both sides, this full reaction is balanced because of those coefficients that we put in front of the compounds. Okay, so we did 5C. Let's move on to 7. So 7 says, colorful fireworks often involve the decomposition of barium nitrate, so we have barium nitrate, and potassium chlorate. Chlorate is a polyatomic ion. And the reaction of the metals, magnesium, aluminum, and iron with oxygen. So the first thing that we're going to start off with is write the formulas of barium nitrate and potassium chlorate. Okay, so we have barium, so that's Ba, and that has a 2 plus charge. And then we have nitrate, so nitrate is also a polyatomic ion, and that's NO3, and that has a minus charge on it. And then for potassium chlorate, we have potassium, which is K plus, and then chlorate is a polyatomic ion as well, and that's chlorine with oxygen, so we have ClO3, and that has a minus charge. And so in barium nitrate, that's what we're starting off with. Let's just make sure here. So barium and barium nitrate will look like BaNO3. But since barium has a 2 plus charge and the nitrate has a minus charge, we will need 2 of the nitrates for the barium. So that's what barium nitrate looks like. And we're not working with any reaction problems here. We're just writing the formulas of what barium nitrate looks like and then also potassium chlorate. And then we'll look at what the next problem is, because then it's the decomposition of some of these formulas. So we're first starting with the formulas to break down the process a little bit more. So we have potassium chlorate, and we first write down the metal, which is K, and then ClO3, which is the chlorate. And since we have a plus and a minus here, they balance each other out, so we don't need to do anything more to these problems. And so both of these formulas are balanced, and we're ready to move on to B. Okay, so B says the decomposition of solid potassium chlorate, so that's what we just worked with, leads to the formation of solid potassium chloride and diatomic oxygen gas. Write an equation for the reaction. Okay, so the solid potassium chlorate, that's what we just worked with. And we know that's the formula for that is Cl or KClO3, and it says that it's solid in that problem. And it also says that it forms a solid potassium chloride and diatomic oxygen gas. So for the oxygen gas, it looks like this. It's just O2, and it gives us in the problem that it's a gas. So we'll write the state of that. And then it also says solid potassium chloride. So the potassium has a K plus charge and chlorine has a minus charge. So it just looks like that, and it's already balanced. We don't need to change any of the coefficients. And it says that it's also a solid state, so we'll put that right on the bottom right. And we have everything written out on the neutral formulas of each different compound and species that we have right now, but it is not balanced yet. So we'll write down what we each have below. So we have the potassium, we have the chlorine, and the oxygen. So those are the 3 different things that we have in both problems. And so it looks like on the left side of the reaction, we have 1 potassium, and we have 1 chlorine, and we have 3 oxygen. So what we'll need to do now is also do the right side. So we have 1 potassium, and we have 1 chlorine, and we have 2 oxygen gas. So it looks like the things that are not balanced here are the oxygen, the number of oxygens. So since we only have 2 on the right side, we're going to put a coefficient in front of the oxygen gas here, the diatomic oxygen gas. But since if we put a 2 in front of the oxygen gas, that would give us 4 oxygen, we have to find the multiple amount of oxygens on the left and the right to which they'll come to the same amount. So we have 3 oxygens on the left and 2 oxygens on the right. So if we multiply both of these with different multiple values, it looks like 3 and 2 will come to the value 6 the soonest. So whenever you have like an odd amount of the same thing on the left and the right, you have to find whatever they will come to the quickest. So 3 and 2 have a value of a 6 in common that they can be multiplied to. That's the lowest amount. So we want to make this the most simple as possible. We don't want to just have crazy amount of coefficients, so that's why we want to be as simple as possible. So to get to 6 on the left side, we have 3 oxygens, so we'll multiply 3 by 2. So 3 times 2 is 6. And so we'll put a 2 on the left side. So what that'll do is that'll change the amount of potassium and chlorine and oxygen. So instead of these, we'll have 2 potassium, we'll have 2 chlorine, and we'll have 6 oxygen. And so since now we have 2 of the chlorine and potassium on the left, we need to have the same amount on the right. So we'll put a 2 in front of the potassium chloride, and then that'll change to 2 and 2. And so since we'll need 6 of the oxygen on the right, we'll put a 3 in front of the gas because 3 times 2 is 6, and so that will give us 6 oxygen on the right. So that's what that looks like when you have to balance these different compounds. You have to think about the multiples of everything and make sure that it's the most simple amount of coefficients as possible that you're putting in front of whatever compound or gas or atom you have. Okay, so that is B. Let's move on to C. And this question says, the decomposition of solid barium nitrate, so we worked that out in problem A, leads to the formation of solid barium oxide, diatomic nitrogen gas, and diatomic oxygen gas. Write an equation for the reaction. So for this problem, we're working with barium nitrate, and we just went over what that looks like. It's just a straight ratio, it's not a straight ratio, since we have two of the nitrates. Since we have two of the nitrates for every barium. So what that looks like here is we have solid barium nitrate, so let's write that down. So it would be Ba, and then NO3, and then we have two of those. And so it gives us in the problem that that's solid, so that's what that looks like for that compound. And it says it decomposes, it doesn't decompose, it leads to the formation of solid barium oxide, diatomic nitrogen gas, and diatomic oxygen gas. So what that would look like for those is barium oxide. So barium has a 2 plus and oxygen has a 2 minus. So these will already be neutralized. There won't be any leftover charge. And it says that it's solid. So we have solid barium oxide, and we're also creating nitrogen and oxygen gas. So for those, we have N2 gas and O2 gas. And those are diatomic gases. We don't have to worry about any of those balances since there's always two of them in itself. Okay, so let's write down what we have on the left and the right. So it looks like the species or the atoms that we have is barium, nitrogen, and oxygen. Okay, so on the left side of the equation, we have 1 barium, and we have 2 because we distribute the 2 to the nitrate. So what we want to do is multiply each of whatever is inside of the equation here. So, inside of the parentheses. So it's 2 times the nitrogen, and then 2 times 3 of the oxygen. So 3 times 2 is 6. So we have 6 oxygen on the left. And so let's look at the right side of the equation, or the reaction. And we have 1 barium, and it looks like we have 1 oxygen here and then 2 oxygen here. So we have a total of 3. And then we have 2 nitrogen. So that's what we're starting with, and so it looks like we have a different amount of oxygen. And so all we have to do, I believe, is multiply, because we want to get 3 more of oxygen. But the oxygen gas here, it's already coming as a multiple of 2. So whatever you multiply the oxygen gas by, it's going to be multiples of 2. But we want 3 more of the oxygen. So it's an odd number. So since we want 3 more, we're going to change the barium oxide, because the oxygen in the barium oxide has a multiple of 1. There's only 1 oxygen in the barium oxide. So we're going to put a 2 in front of here. And so what that will do is that'll bring us up, let me erase all of that stuff, 2 of the barium oxide. And so that'll give us 2 barium on the right, and then 1 more of the oxygen. So we have 2 oxygen right here, and then 2 oxygen right there. So we'll have 4 now. Okay, so now that we have 2 barium on the right and only 1 on the left, we'll need to put a 2 in front of the barium nitrate. So that will multiply everything that we have in this compound here. So we'll have 2 of the barium now, and then 2 of the nitrate. So that'll just double what we have to begin with here. And so that'll look like 4 and then 12 of the oxygen. And so now, now that we're working with only a different amount in the nitrogen and oxygen, I did that on purpose because we're working with diatomic gases at the very last second, or not the very last second, at the very last step, because they're very easy to balance to whatever we need them to be. So since we have 4 nitrogen on the left and 2 on the right now, we need to just put a 2 in front of the nitrogen gas. And so that'll have 4 on the right. And since we have 12 oxygen on the left and 4 oxygen on the right, we'll need to have, I believe, 8 more oxygen. So we'll need to put a 5 here. And because 5 times the 2 is 10, and on right here, we have a 2 times the oxygen on the left. And so 2 plus 10 is 12. So we will have 12 oxygen on the right. So that's what the balancing looks like in this problem. It takes a little bit longer, but you just have to think about the multiples of the atoms that you're working with, because if you have, a diatomic gas, you have multiples of 2 whenever you're multiplying it by. So you have to be strategic on the simplest amount of coefficients that you're going to be using. And let's just say you did a larger coefficient. If you look at these at the end, and all these coefficients that we added to each of these compounds and gases, then if this was 4, this was 4, this was 4, and this was 10, so twice the amount, and you realized, oh, this can be simplified, you can just divide all of those coefficients as long as each one, everything in your left and your right equations can be divided by that in the coefficients, then you can simplify it down even more. But we know that we did this correctly because we have the same amount of everything on the left and the right, and we have the simplest amount of coefficients because we have 2, 2, 2, and 5, and we can't divide by a whole number to get the same thing, or get it simplified down even farther in a whole number. Okay, let's move on to past, I believe we were working on 7C. Let's go to problem 11A. So this problem says, from the balanced molecular equations, write the complete ionic and net ionic equations for the following. Okay, so we're given the left and the right side of the reaction here. So let's break this down as much as we can. So for the complete ionic equation, we are going to simplify any compound that we have that says it's aqueous. So that if it's aqueous, it means its ions are able to be separated from other ions. The ion of itself, of course, will be just floating around because it's an aqueous state. So the thing here we have, I believe this is barium. Let me see what this is called. I think that's chromate. Let me look that up really quick so I know my polyatomic stuff. I believe it's right here. So it looks like it's C2O4 oxalate. So okay, that's an oxalate. Just so that we know what we're talking with here. So that's barium oxalate, and that's a solid state. So solid state compounds do not get broken up because they're solid, so they stay together, so they're not aqueous. So we're going to be attacking or separating these aqueous compounds here into their ions. But the barium oxalate stays alone. It stays by itself. Okay, so it looks like we have an oxalate here, C2O4, And from looking up the charge, it's a 2 minus, and it's an aqueous state. I'm going to put the aqueous just below what I'm writing, just to save on space because sometimes this gets lengthy. Yeah, so that's what the oxalate looks like here. And then it looks like we have 2 of the potassium. And so this time, since it's not in a compound and it's just the ion, that's what I was talking about earlier, that's when you put the 2 in front. And so potassium has a plus charge. And this is also an aqueous state. So we have 2 of the potassium ion. And so for the barium hydroxide we're working with next, we're going to put that in its ionic form. So the barium has a 2 plus charge, and there are no different amount of bariums other than 1, so we only have 1 barium here. And it looks like we have 2 of the hydroxides. So just like the potassium here, we'll put a 2 in front of the hydroxide. So we'll have 2OH minus. And so that's what the left side of the reaction looks like. Let's move on to the right side. And we have also 2 potassium ions, and then we have 2 hydroxide ions because the 2 is distributed amongst that compound here. So I have 2 potassiums, 2 hydroxides, plus and a minus charge, and you always put the charge as well on when you're writing the ionic form when it's in an ion. And then we're working with barium oxalate, and since it's a solid, then we do not put it in an ionic form because it is not in ions in this reaction. So that's what this looks like. So that is the complete ionic form, and we can notice, moving on to looking at the net ionic equation, the net ionic equation really specifies what is specifically happening. So on the left and the right, we may have some of the same things going on, but with the net ionic equation, we can look at what is actually changing in this reaction. So everything else may stay the same on the left and the right, but with the net ionic equation, it's important to know, or it's important to use, because then you can actually see what is the specific change that is occurring. So let's look at the occurrences that we have on the left and the right. So it looks like we have potassium on the left and the right, and it's the same state, so it's both aqueous. And then we have 2 hydroxide on the left and the right. And it looks like that's all of the things that we have in common here. Sorry about that. Okay, so those are the things on the left and the right of the equation that we have. And so now we know what we can cross out and what will be in the net ionic equation here. So what's left over that that doesn't occur on the left and the right, we have the oxalate ion, and we have the barium ion, and that's the left side of the equation. And then on the right, we have the barium oxalate in the solid form. So that's what the net ionic equation looks like for this, because we have specifically the oxalate ion and the barium ion coming together and forming the solid form of those 2 ions. So that's specifically what is changing in this molecular equation. Okay, so let's move on to another example of this. And I believe, yeah. Oop. Let's just get rid of this for a second. Okay, let's move on to 11b. So 11b, we have lead, we have nitrate, and we have sulfate, and we have hydrogen. And so those are the species that we have here. And so we're going to break this down and see which ones we're going to be splitting up into the ionic form. So it looks like we have an aqueous state for the lead nitrate, we have an aqueous state for the hydrogen sulfate, and we have an aqueous state on the right side of the reaction of the hydrogen nitrate. So since we have ions only in those three, we're going to be writing down what those ions will be on their own, but then we're going to leave the lead sulfate here alone because it's in its solid state. So let's break that down. So for the complete ionic equation, we have lead, and it looks like, because everything is balanced here, we can look at an indicator because transition metals, they can have different charges. They can have like a +2 or a +3 charge. So looking at the compound when it's balanced can tell us which charge it was chosen for in that compound. Because nitrate has a charge of minus, because of that, and we have 2 of it here, these ions has a 2- charge, so the lead has to have a 2+. So we know that the lead in this problem has a 2+ charge. And so those are what those 2 ions look like. And since the hydrogen sulfate is also aqueous, we can also break that down. And so we have 2 of the hydrogen, and hydrogen has a plus charge, and let's put an aqueous right below it, and then we have sulfate, and sulfate has a 2- charge. So that's what that looks like on the left side of the reaction. And so on the right side, we have still the solid form of lead sulfate, and that stays the same. And then we have aqueous hydrogen nitrate, so we'll have 2H+, and that's aqueous, and then the nitrate has a minus charge, but we have 2 of it, so the 2 is distributed. 2NO3-. So let's move on to the ionic equation. So let's look at occurrences that happen both on the left and the right that are the same exact ion and that are the same exact state. So we have potassium, or not potassium, my apologies. We have lead on the left, but it doesn't look like we have lead in the same ion form on the right, so that stays the same there. But we do have 2 of the nitrates both on the left and the right, and we also have 2 of the hydrogen ions both on the left and the right. So for the net ionic equation here, we will have Pb, 2+, the lead ion, plus sulfate, 2-, and then that will go to the PbSO4 sulfate. And it's also important to note when you're looking at the net ionic equation that you have the same number of atoms that you have on the left and the right, and it makes sense that nothing is created and nothing is destroyed. So on the left side, it's not like the lead was not there. The lead needs to occur on the left and the right, and it needs to be the same amount of it. So that's what the net ionic equation looks like. Let's move on to, that was 11, let's move on to 30. So 30 is the last problem for today. So the question says, in a common experiment in the general chemistry laboratory, magnesium metal is heated in air to produce magnesium oxide. Magnesium oxide, or MgO, is a white solid, but in these experiments it often looks gray due to small amounts of magnesium, I believe that nitride, a compound formed as some of the magnesium reacts with nitrogen. So that's Mg3N2. Write a balanced equation for each reaction. So it first says that it's going magnesium, and magnesium the metal is going to react with oxygen in the air. So that's our first reaction. And then it says also in the problem that magnesium also reacts with nitrogen in the air. So those are the two different reactions that we are working with. So let's write down what we have. So we have magnesium, that's what it gives us, and that has a 2 plus. And then it says we have oxygen also, so that's a 2 minus. And we also have nitrogen, and nitrogen has a 3 minus charge. So because these are the three that we're working with, this just notifies what we have for the charges when we balance things and when we count up what we have on the left and the right. So we have the first reaction, which is the magnesium, and it said it's in its solid state. So we have magnesium, and that's a solid state of that. And then we have oxygen also in the air. And so whenever oxygen is in the air, that's in its diatomic gas state. Since it can't just be oxygen alone, there's 2 oxygen. That's why it's diatomic. So diatomic, that means two of the gas. So of O2, and then what that creates, it said, is MgO. And Mg, that has a 2 plus, and then oxygen has a 2 minus. So 2 plus and a 2 minus, that already balances each other out. And it says it's a solid powder that it makes, so that's a solid state. So it looks like everything is already, nothing, no, it's not balanced on the left and the right. That's why you always double check. Yeah. So we have magnesium and oxide, or oxygen or oxide. And then we have magnesium and oxygen here. And it looks like we have 1 magnesium on the left and 1 magnesium on the right. And for the oxygen, it looks like we have 2 on the left and we only have 1 on the right. So we are going to put a 2 in front of the magnesium oxide on the right, so that will change these both to a 2. And so now, since we only have 1 on the left, we're going to put a 2 in front of the magnesium. And so there will be 2 of everything in this reaction. So that is what the first reaction looks like. And it also says to look at the reaction of when it reacts with nitrogen gas. And so it'll be very, very similar to what we just wrote down. So we have magnesium in its solid state, and it reacts with nitrogen in the air, and so that's also diatomic gas, and so that's N2, and that's a gas state. And it's said that it forms Mg3N2, but just to double check if they balance that correctly, nitrogen has a 3 minus charge, so that's 2 times n minus 3. And magnesium has a 2 plus charge, but there's 3 of them. So that's 3 times 2. And so adding all these up, that should be 0. So we have 6 here, and then we have minus 6 here, so 6 and a minus 6 is 0. So they wrote it down correctly in terms of how much they have of each atom, and it's already neutral, so that's good to know. So magnesium nitride, that has a solid state as well, since it said it's a gray powder. So now let's balance everything. So we have magnesium and nitrogen, so those are the 2 different atoms that we have on the left and the right, and it looks like we have 1 of the magnesium and 2 of the nitrogen on the left, and we have 3 of the magnesium on the left, and we have 2 of the nitrogen on the right. 3 of the magnesium on the right and 2 of the nitrogen on the right. So we have a different number of magnesium here. So that's the only thing that we're going to change, and since magnesium sits alone, it's a very simple balancing. So we'll just put a 3 in front of the magnesium to get 3 magnesium on the left. And now we have 3 magnesium on the left and the right, 2 nitrogen on the left and 2 nitrogen on the right, or left and the right. Okay, so that's all about the balancing techniques and writing down these reactions. And it's also important to note of going through this process a bit slower, because sometimes you can miscalculate things because it's simple math, so sometimes we can make simple errors. So just double checking what we did and going through our calculations and balancing a bit slower can really help. And yeah, just making sure that you're writing things clearly and correctly. So that was the last problem. Let me know if you want to go over any of these problems again, and if any of the processes that we went over were a bit confusing at all. But that's all we have for today, and I hope that this helped you, and your weekend and your next week will be wonderful, and I will see you all next week. Yeah, of course.